First things first, let's correct the problem we were working on yesterday. The problem that took us, I feel really bad because this problem really took us it took us at least an hour on Monday and a lot of the day yesterday. And the problems in general don't take that long. It's just that I think the one that the book gave in particular was the numbers were a little bit harder than what they needed to be, especially with 3-digit numbers. So let's see. Let me pull up the notes here. So if we go through our notes, just a real quick touch base on this. We were talking about diagonalization and how conjugation gives us this nice process where if I'm given a matrix that is not nice looking, that we were going to have a bad problem actually computing the characteristic polynomial, let alone factoring the characteristic polynomial, we can use this conjugation methods to sort of mimic our row and now column operations to get the matrix at least in a triangular form, and then if not, potentially diagonalize the matrix. So here is our matrix. And I was looking through it, and our first two steps were good. We just made one mistake. So this was step one. And then we did our step two. We found our second elementary matrix, and we performed those row and column operations. And that was good. And then we made one mistake going from here. So we got to here, and then once you find a few zeros and you're down to like the last few positions that you're trying to get rid of, we kind of got to this point where we saw, well, doing elementary row operations may not necessarily work based on just considering the row operation, because the column operation then will get in the way. And so we had it right. And then on the next page, what did we do? What did I do? We tried it again, and basic transcription error. So careful with this. It happens, right? Especially rewriting and writing these same matrices over and over. Not only can you make an arithmetic error, sometimes you just write something down wrong and you forget one little minus sign. And so this is all we forgot yesterday. And as we saw at the end, once we finished this problem, we were checking our eigenvalues and eigenvectors that we should have gotten from this process. And what happened? It didn't work. So it was a dead giveaway that we did something wrong. And we didn't have time I didn't want to spend time on class chasing that out. So I was looking at it yesterday and realized all we did was miss this tiny little minus sign. It didn't actually affect our next process. So our next process was to get rid of this 10. So our E3, our third elementary transformation, was still the same. It actually is just going to change that fourth one. So let's see. So the rest of those notes are fine. And then we got into everything else. So let me go back through it again. And here, let me just pull up these two pages. So here I reworked the problem. So from this page here was our A, our E1, our E2 are the same. Actually, I might have flipped those. I think we might have done this one first and then this one second. These two commute, so it doesn't matter which ones we do in that order. And then that E3, we had the E2 there, and then the E4 is going to change this guy to a -3. And then, of course, we showed that applying that sequence of operations in conjugation is going to diagonalize our matrix. So write that down if you guys want, or I think I'll scan these and upload them to the Google Drive to put them in our notes collection, so you guys can always look that up if you want to look through it. But then our P calculation is going to change. And so here's our P inverse calculation. So since just by the way we were labeling our P's and P inverses, again, it doesn't quite matter when you're diagonalizing the matrix, which one is P and which one's P inverse, as long as your position is correct when you're checking and doing it, right? We could have labeled this guy as P inverse if we wanted and labeled this guy as P. That's how the book does it. It doesn't matter though which one you label, as long as their positions are correct. And so when we're computing the one on the right, so the term on the right that follows the matrix A, that's the one that gives us our eigenvectors and eigenvalues. So there's our step one, E1 or E1 inverse, E2 inverse, E3 inverse, and then now our new E4 inverse. Computing those, just be careful with going through those computations. Again, easy to make mistakes on all of those. And then here's our vectors. And now this is rather difficult to check, right? Because now if we were to actually check this, remember our matrix A, see if we can put both of these on screen here. Our matrix A was this, and so checking it, it's a pain. This is kind of a bad example to be in the book, because we would want to check that this column vector 7, 2, and -4 is an eigenvector for this. So now I want to multiply A by 7, 2, and -4 by that vector and see if we get a scalar multiple of 7, 2, 4, -4. And namely, the scalar multiple we should get is 3, because this first vector is going to correspond to the first eigenvector or eigenvalue in the diagonalization. So run through those computations. It's going to be a little hard because you've got these 105s. That's really where it starts to just get tedious, you know, because now you're multiplying these scalar multiples of 105, 33. You're basically doing an inner product of that row vector with this column vector. Numbers are pretty big, but it should work out. You should kind of see. So if we have two copies and -4 copies of 105, that'll give us -2 copies. So -210. 7 times 33 is going to be 210 plus 21. And so those 2 10s will cancel out and we'll just get a 21, at least in the first position when we multiply. And that's 3 times 7. And then go through the other calculations. And you should be able to check that those are, in fact, the correct eigenvectors formed by the columns here. Any questions on that? So again, you will have to do a problem like this. I almost feel bad putting a problem like this on the final because it did take us a while to get through in class. But again, I think in general, they're not too bad, right? Elementary matrices and performing row operations is pretty basic. The only extra caveat now is now we're also doing the corresponding column operations and finding those last positions, finding those last couple of the row and column operations. You got to be a little bit more clever in how you choose to do those. So I think that's a good thing to test over. The numbers of the problem I worked out aren't as bad. They're not 3-digit numbers. And so they're definitely within the realm of computation. And the other thing I did, so one part of the problem is to check your work. I mean, I encourage everyone to always check their work. Some of you guys have been, but I also understand the fact that sometimes it's hard to check your work if you're pressed for time, you know? So part of the problem is to, once you compute this matrix P and P inverse, you can determine the eigenvectors, determine the eigenvalues, you can determine the dimension of the eigenspace, all that good stuff. But then one of the last part of the problem is to like check your work. So check that the columns of this P inverse matrix you found are in fact eigenvectors. So multiply that out, check you get the correct scalar multiple. And I'm going to give you guys points for that. I think it's, in a normal job, you're going to get paid to check your own work, to cover your own mistakes, especially if you're computer science, you end up programming something, right? Half of the thing you're getting paid for isn't just creating the program, but also debugging the program and making it work. So that's kind of in this vein, right? We should give you guys points to check your work to make sure you're doing it correctly. And then, of course, that'll help your overall grade for the rest of the problem as well. So I think that'll be good. I think most people did really well on the eigenvector problem on the last exam. Of of course, a little more basic in terms of just pure computing in terms of the characteristic polynomial. This one, you're going to be, there's some freedom of choice of how you approach the problem in terms of what row operations you do. And then at the end, you got to be clever to make your row and column operations work out. So in terms of abstract problem solving techniques, maybe a little harder with this guy because it's not just purely algorithmic and purely straightforward. But in terms of the quickness, I do think it is a little bit quicker, especially with some of these more complicated matrices, because you'll get it within 4 steps. So I'll give you that much as well. So it shouldn't take you more than 4 elementary matrix operations to diagonalize a matrix, especially the matrix on the midterm. The other standard problem that's going to be on the midterm is to create an orthonormal basis. And that's what we're going to talk about today, the Gram-Schmidt process. So as we go through this today, there's going to be a problem exactly like one of the examples we do, or at least different numbers, different vectors given, but you will have to start with a basis or start with a linearly independent set and create an orthonormal basis from it. Very standard. Got to check to see if you guys can do that. Not too difficult though. I think the algorithm's pretty straightforward, and it's only going to be, again, 3 by 3. Most of the stuff we're doing is in R3. R3 is a nice where it's complicated enough that you do have to do the work. There's not as many shortcuts. R2, you can get a lot of shortcuts. So you do have to follow the process and follow the algorithm, but it's not too big where you're just wasting time going through it. Okay, so where did we leave off yesterday? I think we defined an orthogonal basis and a normal basis. Now my notes are all jumbled around. We were talking about determinant and trace, how those can give us some shortcuts in finding eigenvalues. So here was our notes from yesterday. Orthogonality and Gram-Schmidt. This was like kind of a summary of the class and a lot of this section in chapter 4. Everything about these concepts of rank, linearly independence, dimension of the image, dimension of the span, kernels, bases. Excuse me. And the last thing we were tying in is, well, we want to tie in our length and our orthogonality. And so we went over those definitions again. And so we've got to tie in this dot product, and we'll tie in projections as well. So dot product intrinsically tied in with this notion of projecting and finding orthogonal projection. So we saw earlier this semester of how if I'm given 2 vectors, I can project one vector onto another vector. Today, we'll expand that a little bit and talk about how we can actually project a vector onto a vector space. But before we do that, we have to, be able to figure out how do we create orthonormal sets, or even at least how can we create orthogonal sets. So remember, we have an orthogonal set if every vector in the set, if I take their dot product, we're always going to get 0. Every vector is mutually orthogonal to all of the other vectors. Of course, it's not orthogonal to itself. And then we can create an orthonormal basis or an orthonormal set if every element in the set is not only orthogonal to the other ones, but each element is of unit length. And that's going to be our goal for today. This is the idea behind the Gram-Schmidt process. So I'm just going to start by example. I think the best way to do this is to see the example, especially if this is a non-math major course. If I start writing out the algorithm in abstract mathematical terms, I think I'll just lose some of you guys. Especially at your level, I think it's better to kind of learn the process, learn the examples, and then have that build into your mathematical abstract repertoire. It kind of, when you try to learn the abstract math, after you kind of already know some examples, you can tie in the abstract language with the examples you already know and how it works and make sense of the abstract language better. So if you're kind of getting into some higher math where you're getting a little more abstract, that's a good way to learn some of the language in general. Always lead by example, especially at your guys' level. So given a set, usually we have at least start with linearly independent set. You don't have to start with a linearly independent set, but if you don't start with a linearly independent set, all you got to do is throw out the vectors that you don't need. So if you have too many vectors that are non-linearly independent, you can always throw some of them out and reduce the number of vectors until you get a maximal linearly independent subset. So we're going to assume, at least given a linearly independent set, we want to create an orthonormal set. So let's give our set a name. Let's just call it capital V. And let's start with some vectors in R3. So let's do something fairly simple. Let's say 1, 1, 0, 1, 0, minus 1. And what's our last one? Do we want 0, 1, 1? So unfortunately, I did not have time to work out an example explicitly for this before class, since the process is fairly easy. I'm just trying to think at the moment to see if this is sufficiently complicated enough. Let's put a minus sign here that it will illustrate the process. So none of the vectors are mutually orthogonal, which is going to be good. Okay. This will work. And then I think we'll have more examples. I think this should be a good example to start with. It won't take us too long because then we're going to apply this process and we'll see it a few times in context. So the first thing is going to be to pick a starting vector. Doesn't matter which one you pick in your set, but be sure to label this. So this will help me grade you guys. Just try to keep your work organized so that I can kind of follow your steps of your algorithm. Think of your writing your math problems like writing code. You want someone else to be able to look at your code and understand what your code is doing if they need to build off of it. So think about it for me, for my sake. I should be able to follow your written mathematical work to see where your mistakes are, where your thought process is going, so I can give you all the points. So pick a starting vector. Doesn't matter which one you start with. So as you see more complicated examples, you always want to kind of pick the easiest vector to start with usually. And what do I mean by the easiest vector? Usually the vector with the smallest numbers, the most zeros, is always a good one to start. These ones are all essentially the same vector, right? They all have 2 1s and a 0 in it. So let's just go ahead and pick this guy as our starting vector, and we'll call that V1. Now, one thing I'm going to skip over is how do we create what do we call it? A normal set. So how do we normalize a set? That's pretty basic. I'm going to leave that to you guys because the first thing we want to do in our first step is to normalize that vector. And I think we've seen how to do this. I don't know if we've addressed it in particular. But all we do is to take V1 and let's see, what's the best way to label these? let's just use different letters. I'm worried we're going to run out of letters. So we'll take our V1. The first thing we're going to do is to take U1 and take whatever the first vector is and normalize it. So make it unit length. So all we do is take the vector and divide by its length. So let's use our U's. U is going to be our ending vectors that we keep within this orthonormal set. And so all you got to do is compute the norm of V, norm of your starting vector, and then divide by it. And for the sake of computation and organization and just visual niceness, you can keep it like that if you want. If you want to keep the scalar multiple, like if you have nice integers in the vector and usually the norm of the vector, sometimes it's a square root, oftentimes it's a square root. If it ends up being a whole number even, you'll end up getting fractions within the entries. So if you just want to keep that fraction or whatever multiple outside, I'm perfectly fine with that. It will actually save a little bit of effort in writing and hopefully reduce some of the visual mistakes that happen, some of the transcription errors, as we've seen, can happen just writing the wrong thing down. So easy enough. Now, this vector is of unit length, right? The norm of this guy times or divided by that guy will end up giving us a unit length vector. So then we're going to pick a second vector. And what do we want? We need this vector perpendicular to the first. And how do we do that? So if you remember way back when we were in this chapter, when we were talking about dot products, we simply break our vector down. So let's give our vector first. So our V2, let's go ahead and write it. 1, 0, minus 1. We can break this vector down into a parallel and perpendicular component in terms of the direction of U1, i.e. we actually don't even need the parallel component, but you have to compute it anyway, since that is how we find the perpendicular component. And so we would just take V2. Sorry, let's call that V2 perpendicular. So we'll have an extra subscript there. We just take the vector and then we subtract off the parallel component. And remember that the parallel component is just going to be the projection. So minus the projection onto U of V2. So this is our algorithm. Let's pick out the pieces. So the biggest piece we need to compute is going to be this guy here. So let's go ahead and compute that. Now, nicely enough, if you remember the formula, it's going to be U1 dot V2 over the norm of U1 squared in the direction of U1. And nicely enough, since we normalized U1, that denominator is going to be 1. We already know that norm of U1 is 1. But of course, how did we normalize U1? We really just borrowed it from V1 and divided by the norm. So like we're still going to have that coefficient, this factor of square root of 2 come up within this calculation, and it will appear twice, both in here and in this term as well. So we go ahead and compute with the dot product. So I'm going to keep out the 1 over square root of 2, and then in our parentheses we'll have Here, you know what? Let's get a new piece of paper. Linear algebra. I think I've used more scratch paper for this class than like any other math class. Calculus problems don't take nearly this much paper. So projection on the U1 of V2 is U1 dot V2 over a norm of U1 in the direction of U1. And so we've got 1 over square root of 2 times our U1 was 110. And we are taking a dot product with V2, which was 10 minus 1. Now this norm of U squared is 1, so I'm not going to divide by anything. But we do going to multiply this times U1, which was 1 over square root of 2, 110. So those factors of 1 over root 2 are going to show up again. But nicely enough, since they are scalars, all scalars in all of these operations, hopefully you've picked up on that from linear algebra, this course being linear and linear operations, scalar multiplication is a linear operation. We can always kind of commute that operation with everything. So we can pull out the scalars. It'll just give us a 1/2. And then now if we take our dot product, what do we get? Just a 1, easily enough. And then 110 for our vector. So all in all, our projection is going to be 1/2 in the direction of 111. Now this is the parallel component. So our V2 perp. And actually, you know what? I'm going to put the perpendicular sign up top just to make it a little nicer. It's just an indicator. It's not a really important script. So whether it's a superscript or subscript, doesn't matter where you want to place it, as long as it's kind of clear what you're doing. So we want to take V2 minus V2, and I'll put the parallel up here. And so what are we going to get? Our V2 was 10 minus 1, and now we want to subtract off. I'm going to go ahead and put the 1/2 in there, just since we're subtracting off component-wise. And we get 1/2, 0, and minus 1. Did I miss something? I did. I'm like, something's not right. This should be a minus 1/2 here. Gotta remember that, minus 1/2. And then, of course, you can always check. So just a little side scratch work. You don't have to do this at this step. But again, I always encourage you guys to check your work. Check that V2 perpendicular dot U1 is 0. We're going to have 110. Now dot product with 1/2 minus 1/2 minus 1. And so that's just going to give us a 1/2 minus 1/2. So we've created a perpendicular vector. So far our set is going pretty well. We start with one vector, it's normalized. Great. Now the next vector, what we want to do is just pick off the perpendicular component to that first vector. And since now I have two vectors that are orthogonal, the first one's of unit length, the second one is orthogonal to it, but it's not unit length. So what is our next step? Is to just normalize. So the second basis vector that we want, or the second orthonormal vector we have in our set, is just going to be the perpendicular component divided by its norm. So let's go ahead and, I guess, compute that first. Let's see. So V2 orthogonal normalized is going to give us the square root of 1/4 plus a fourth plus 1. So square root of 3/2. Not a terribly nice number. So our U2 is going to be 1 divided by square root of 3/2 times our 1/2 minus 1/2 and minus 1. So I highly encourage you guys to simplify your work. And at least one rule for simplification is you should never have compound fractions. So you should never have a fraction within a fraction. So let's simplify this, and for the sake of keeping constants outside, this is going to be square root of 2/3. So 1 over square root of 3/2 is going to be square root of 2/3. And you can make these integers if you want. If not, you can keep this like this if you want and then move on to the next vector. But again, for the sake of making things look a little nicer, I like to keep the vector coordinates as integers. So I'm just going to go ahead and factor out a copy of 1/2 because that'll simplify a little bit with this square root as well. Maybe we can get it looking a little nicer. So we'll have a 1, a minus 1, and a minus 2 here now. And then all in all, our simplification, we have a square root of 2 just for the constants. So little side scratch work. I think most people are actually pretty good with some of the simplifications I've seen, which is good. Unfortunately, I'm going to teach a couple sections of pre-calc in the fall, and some of this is a pain to get through. Most of you guys are pretty good though. So of course, square root of 2 and that 2 is going to give us a square root of 2 left over in the denominator. Square root of 2 times square root of 3 will give us that square root of 6. So we can write it as 1 over square root of 6 times 1 minus 1 minus 2. So we've got integers in our vector, and then the constants out front are simplified. So again, I do want you to simplify it. Don't keep compound fractions, and I don't know, I would also kind of recommend at least some sort of consistency with the way you are simplifying it, because if we want to keep constants out front of the vector, I would say keep that consistent. You don't want to keep constants out front of the vector and still have fractions in here. That's kind of inconsistent. So pick one. Either keep, multiply everything through for each term, in which case we would have to simplify each of those, or, factor out your fractions to keep constants, keep whole numbers in your vector positions, and then simplify your constant out front. For me, I think that's the easiest way, the most simplified way. Okay, so what have we created now? We've created two vectors, u1 and u2, that are both unit lengths. And orthogonal. So what do we do for the next step? Well, this is where it actually gets tricky. So the third one and then beyond is where it starts to get a little more complicated, because what we want to modify V3 now so that the result is orthogonal to both U1 and U2. So it's actually not too complicated. So what we're going to do is repeat step 2. with V3 and U1, then use that result again, repeating step 2 again with the result and U3, and then finally, since the result of that will now be orthogonal to both. Sorry, this one should be U1 and this one should be U2. Sorry. The result will be orthogonal to both U1 and U2, and then we're going to repeat step 3 and normalize it. So just some extra work. The process is the same. We know how to find orthogonal components. We just need to make sure it's going to be orthogonal to both the previous vectors that we created. So our V3 was 0, -1, and 1. Our U1, let's go ahead and rewrite all these, was 1 over root 2. Uh, 1, 1, 0. And our U2 was 1 over root 6, 1 minus 1 minus 2. So we're going to pick V3 and U1. We want to subtract off the parallel component from V3, and so only get the orthogonal component of V3 from U1. So we'll get projection to U1 of V3 is going to be V3 dot U1 in the direction of U1. So I'm not even going to write that denominator. Of course, we want to divide by the norm of U1 squared. But since we've created our orthonormal basis, they're of unit length. So we don't really need that. So let's go ahead and compute our dot product. So what is that going to be? Our dot product, we're going to have a 1 over root 2 from that component. We'll have a 1 over root 2 from this vector. And then the dot product now of the vector components is going to give us a -1 in the direction of U1. And again, that scalar was here. So all in all, we've got 1 over 2, -1/2 times 1, 1, 0. And so to find the perpendicular component, V3 perpendicular, this one's going to get, notation-wise, it's a little hairy. So try to just be clear on your notation. Of course, this perpendicular means perpendicular only to U1 at the moment. We are going to take V3 and then subtract off the perpendicular component we found, or the parallel component we found, excuse me. So we're going to subtract off -1/2, 1, 1, 0. And what are we left with? So that'll make it positive. We'll get a +1/2 here. We'll have negative plus 1, so that'll give us a -1/2. And then just a 1 here still. So if we want to pull out our constants, or 1/2, 1 minus 1, and 2 now. And again, just as a side, if I take this guy and now dot product with U1, what's the dot product going to be? It'll be 1 minus 1, 0 times a scalar. So it'll give us 0. So this is going to be perpendicular. We don't want to normalize yet, though. Because even though we have a vector that's now perpendicular to u1, it's not necessarily perpendicular to u2. So let's maybe call this something else. Let's call this w3, just to not have so many scripts and subscripts and superscripts on our indicators. And so now what do we want to do? We want to take that result and we want to find the perpendicular component of that with u2. So we are going to project onto u2 our w3. And so this will be w3 dot u2 in the direction of u2. So we are going to get a 1/2. We're going to have our w3 integer components where 1 minus 1, 2. And then our u2 was, we had in the dot product, we'll have a factor of 1 out of square root of 6. And then in this guy, we'll also have a factor of 1 over square root of 6. So dot product with 1 minus 1 minus 2 in the direction of 1 minus 2 minus 1. Sorry, I'm minus 2. So what happens when your eyes are wandering while you're trying to write is you write the wrong thing in the wrong position. Yeah, so we had 1 factor of square root of 6 with this guy, 1 factor of square root of 6 with this guy. So that just gives us 1 over 6. So the constants are working out a little bit better now. So hopefully everyone can kind of see that. That way we're not getting bogged down with square roots and different square roots within the components. So what are we going to get? 1 over 12. And then when we compute our dot product, we've got 1 plus 1 minus 4 in our direction of 1 minus 1 minus 2. So that'll give us a minus 2 over 12 will give us a 1/6, a negative 1/6, 1, 1, 2. And the second one and the 2 are negative. So that's our projection. Now our perpendicular, so our third and final vector. Actually, sorry, we've got, I guess, 2 more steps. This is our projection, right? We want to find the perpendicular component first. This was our projection. So our perpendicular component is going to be W3 minus that projection. And let's see, what was our W3? Was 1/2, 1 minus 1, 2. And we want to subtract off our negative 6, 1/6, 1 minus 1 minus 2. I guess if you wanted to rewrite this and get rid of the negative out front, you could always distribute the negative at least to keep these as integers, but not have to deal with extra minus signs if that's getting in the way. Either of those are fine though. Okay, so W3 minus the projection, and what are we left with? This one does not look nice. So now it looks like we actually need our components because we'll have a 1/2, a minus 1/2, a 1, and then we'll have plus 1/6. We will have minus 1/6, and then minus 1/3. So what do we get? It's going to be 4/6, so 2/3. This is going to be negative 4/6. And then 2/3 here. So all in all, those numbers not ending up too bad. And that's what we got. Now, we got one more step, but at this point we can check, do we get something that is orthogonal to the other two vectors? So remember our other two vectors, see if we can put that on screen, or these two here at the bottom. So if I take a dot product of this guy and this guy, the nice thing again about dot products and keeping the constants out is we can kind of ignore the constants and take the dot product of the actual vectors. So we will have 1 times minus 1, or sorry, 1 plus 1, and then minus 2, so that those two will be orthogonal. And then will these two be orthogonal? Looks like it will, because we'll have 1 and minus 1. So this guy is now mutually orthogonal to the first two, and we only have one more step. We just need to make it normal, so make it unit length. So our U3 is going to be the perpendicular vector that we found divided by its length. So the norm of W3 perpendicular is going to be 2/3 times square root of 1 plus 1 plus 1. So that's going to be 2/3 times square root of 3, which you can leave like that, or if you want to write it as 2 divided by square root of 3 for a little bit less writing. Of course, we're going to divide by that. So now our U3 might almost actually be better to keep it in that form, because what do we have? We will have 1 divided by 2/3 square root of 3 as the reciprocal of the norm times 2/3 1 minus 1 1. And so this 2/3 and that 2/3 will cancel, and we'll just get 1 over root 3 1 minus 1 1. Everyone follow? So now, all in all, let's go ahead and summarize it. Our sets, our orthonormal set, I'm going to call it B, since we do have 3 vectors in R3. They are linearly independent. They are orthogonal, and so it will be a basis, is going to be 1 over root 2, 1 1 0, 1 over root 6, 1 minus 1 minus 2, and now 1 over root 3, 1 minus 1 1. So easy enough to check when we're computing the dot products. We can just we can pick out the vector components with the integers and compute the mutual dot products. So we've checked those, shown that those are all 0 pairwise. And then of course, now if I take a vector and normalize it, well, this will be 1 squared plus 1 squared under a square root. And so that will make it unit length. So the constants out front will work for that. And that's all there is. So question, what would we do if we had a 4-dimensional space? We can essentially just keep repeating this process. So hopefully that algorithm is clear. We would essentially now take our vector 4, subtract off the perpendicular component to this guy, make it parallel, or subtract off the parallel component from this guy, subtract off the parallel component from this guy, and subtract off the parallel component from this guy. And then what is left? Something that is going to be orthogonal to all of those. So some shortcuts in that regard and that we could have taken. So let's take a look. The first step is pretty standard, and the second step was pretty standard. So for the first two vectors, there's basically nothing else you can do. However, for the third one, you can start to take a few shortcuts because namely when we want to, we can, what am I trying to say? We can almost ignore this scalar component here. All we are trying to do is from vector v3, create something that is orthogonal to u1. So on this step here, we found the vector that is orthogonal, and then it kind of had this factor of 1/2 here. And I already know that if I take this vector here and take a dot product with this guy, they're going to be orthogonal. This is just an arbitrary scaling factor. It is kind of giving us that specific component of v3. But if we had ignored that factor of 1/2 and just moved on to the next step, what would have happened? Well, we would have just kind of ignored that factor of 1/2 here, but the dot product of that component still would have been the same. So we're still going to end up subtracting off a given component. Actually, let me think about that. That should work since u1 and u2 are already orthogonal. And then essentially what's going to happen is that scalar will re-show itself ultimately when we try to normalize here. Right, so our next step then, what did we find? We took w3 and now found the component of that. So we took w3 and projected that onto w2 and subtracted off that component to create something normal to both of them. But again, now this constant out front, as we kind of saw, didn't matter, because what happened with this constant when we normalized, it really just went away. And it's almost like if we would have just started with 1 minus 1 and 1 and didn't have this scaling factor, when we then normalize, we would just simply divide by that 1 over square root of 3 again. So there are a few little shortcuts you could try to take in terms of like ignoring some of these scaling factors if you want to try to make your computations easier. I would just say be a little careful with doing that. The other thing we could have done is instead of taking W3 here, I guess this could be a little bit of a shortcut or just a different way to work the same process. When we get to our third vector, we need the component of our third vector that is orthogonal to both u1 and u2. So what we could have done, so let's put a double star here. Just for an alternate method. And this might be a little quicker, might not. Is to take v3, subtract off the projection onto u1, and subtract off the projection onto u2. So we could kind of do those two steps simultaneously. What we did is we did this step first and called that W3. And then I found the projection of W3 onto U2 and subtracted that off. You could just straight up work with V3 and subtract off both of those projections. So if we kind of go through that real quick, our V3 was 0, minus 1, 1. Our projection onto U1 of V3 was negative 1/2, 1, 1, 0. And then our projection onto U2, So that was this step here. Now our projection onto U2 of V3, we didn't compute because we used W and projected that and then subtracted that off. So the other thing we could have done was now compute this projection. So that's going to be, let's go ahead and compute it. Make sure we keep our parentheses here. So we want to do 0, -1, 1, dot product with our U2, 1, -1, -2. And so here was our U2. We had already found it, and our U2 had a factor of 1 over square root of 6. And then, of course, we want that in the direction of U2. And so we would get those 2 factors of square root of 6 again. So same computation, except now instead of finding W first and then computing the subtracting off the next component, we are simply sticking with our V3 here and subtracting off both of the parallel components simultaneously. So when we do that, we will have our V3 minus -1/2 110 minus. And now when we compute this, so what was our dot product? It looks like we got 1 minus 2 was -1. So it'll give us a -1/6, 1 minus 1 minus 2. Did I get all the minus signs correct here? Uh-oh, hold up. Our U2 needed that minus sign there, didn't we? Always careful with the minus signs. So that minus sign, it's actually not going to change much other than changing the direction. So that would have put a minus sign here. And then now when we take the dot product, we will get another minus sign, and that would have made it positive there. And so what do we get? Let's go ahead and compute that out. We should get the same thing up to maybe a plus or minus direction. Might be wrong if we messed up one of the minus signs. But regardless, if we change the direction, it will still give us an orthonormal set. And then now this one will be minus 1/6 minus 1/6 and minus 2/3. So what are we going to get? We're going to get 1/2 minus a 6.
Shouldn't that just be minus 1/3?
Yeah. Thank you. And then we're going to get -1 plus 1/2 is -1/2 plus 1/6. And then we will have 1 minus 1/3. If everyone's kind of doing those numbers, we're going to get a 2/3 minus 2/3 and a 2/3. So we get the same thing. So same thing at that kind of before normalization, before we repeat step 3. And then, of course, when we normalize this vector, we would get that guy there. So this method might come in more handy. I kind of like the other method since it's a little more like one at a time. Though, of course, this one, since you're doing both, you do just got to be careful of keeping track of everything at once. And then this method actually might even be better because what's going to happen if we have 4 vectors or more? Well, with our V4, we would just take our 4th vector and now subtract off we would take, let's call it V4 perpendicular. We would just take the fourth vector in our set and subtract off all of the projections. So the projection onto U1 of V4 minus the projection onto U2 of V4, and then subtract the projection onto U3 of V4. So this would be our step 2 repeated, and then step 3 is normalize. And then you would just keep doing that for however many vectors you have in your set. Oh, sorry, that was off screen there. Any questions on that? So take a look at, let's see here. I'll just share the screen. I don't want to have to write it out since I kind of want to move on. But the book has the algorithm here summarized a little bit more abstractly in terms of mathematical notation. Now, keep in mind when you have your V2 is going to be U2 minus that. They don't really quite define what U2 is. So I don't know, dissect that mathematical language, but you can kind of think of, I think actually, no, sorry, they use different U's and V's. So switch around the U's and V's from what we did. So they first create an orthogonal set and they don't do the normalization part. This was what I was kind of saying in terms of the scalar multiples, where you can kind of ignore some of those scalar multiples that we were getting when we were normalizing. You can create an orthogonal set from the get-go, which is what they do here. And so they start with a vector, start with any vector, keep it, then take for vector 2, subtract off the orthogonal component, or the parallel component, excuse me. For the third vector, subtract off the parallel component from the first one and the parallel component from the second one. And you just do that for all of your vectors. And then at the end, you can go through and normalize. So however you like to do that, there is a little bit of leeway. As long as you kind of understand the process, the key thing is creating the orthogonal components. Normalization, I did it as we went. But you can save that for the end if you think that's a little quicker, if you don't want to deal with some of those constants and fractions out front. Any questions? Okay, so why is this useful? Let's see, do we want to talk about planes and orthogonal components? We've got about 25 minutes. And I want to get into orthogonal bases and orthogonal sets. So let's talk about Fourier expansion and orthogonal projection. It's going to be our application to this. So the key thing with a lot of these and creating our bases is actually creating the orthogonal set. Orthonormality, it's nice, but the normality isn't absolutely required when we're looking at projections onto spaces. So remember how we've described bases as giving us, and unfortunately it's hard to draw these in 3 dimensions. So the best examples are 2 dimensions, where we consider our bases vectors as creating a grid for our space. So our one basis vector, we can take scalar multiples, but then we can also walk along the direction of the other basis vector. So if we walked, let's call this guy u and this guy v here. So I could walk in the direction of u and then walk as many times as we want in the direction of v. And so it's going to give us these grid lines for our space. But if we just have a general linearly independent set, as we can kind of see, the grid lines can be like skewed. They're going to be parallelograms. If I could draw my lines parallel. But they're not going to be rectilinear. They're not going to be squares or rectangles at least. And so this is what the orthogonality process does. If our basis vectors or our linearly independent set is an orthogonal set, then at least we know that the directions are mutually orthogonal. And why is that helpful? Well, if they're not orthogonal, you can kind of think about, well, it's not necessarily unique in some sense, or it's not like I'm purely walking in the direction of v, if that makes sense. Like if I walk along v, I'm not walking purely in the direction of v. There's a component of v in the direction of u. We can orthogonally project v onto u. And so even though I'm walking in the direction of v, I'm also walking a little bit in the direction of u. And that can screw some things up. So for example, if we have some plane, and let's say the grid lines on the plane are skewed. So now I'm trying to draw a three-dimensional drawing. Let's say here's the origin. Let's say this is our 0, 0, 0. And let's say we have some point P outside of the plane. Well, now what we want to do is to potentially find maybe the distance from P to this plane. So we've seen problems like this before. And now we're just going to have maybe a little bit stronger tools and methods of approaching this. So what we would like to do is to find this component here. So let's call P, let's actually call it Y. I think that's what the book calls it. And let's call Y the directional vector. So the nice thing about subspaces, as we know, is that they always contain the origin. So we have our W as some subspace, a plane through the origin. And so we're going to have some point P, which we can think of as a vector from the origin to that point. And well, if we want to find the distance, what do we need? We need the orthogonal component. So let's actually call this vector z. So if we want the distance between, let's say, y, representing, y is the vector, the directional vector representing the point P, to the plane W, we need the length of y minus z. In other words, this is the perpendicular component of y, where our z, it would be what we would call v parallel. It is the parallel component, sorry, I'm switching letters there, y parallel component of our vector y in the plane W. So we can kind of use this Gram-Schmidt process to help ourselves solve this problem and find these components. The problem is if we start off with grid lines that aren't orthogonal, then in some sense, the components of our z are going to get in the way. So let's draw these as like really skewed. In other words, if the basis that we choose for W isn't orthogonal, well, how are we going to represent Z? Well, we can represent Z as a linear combination of those two vectors. But finding that linear combination, well, it would take some work and it would take a lot of effort, namely because it's not going to be as simple as finding the projections of, say, this vector onto each of these vectors. Right? Ideally, what we want to do, if you kind of got the gist of this, of the Graham-Schmidt process of taking one vector and subtracting off parallel components in order to find an orthogonal component, the key thing that makes this work is the fact that the vectors we created before the step we were on are mutually orthogonal. If U1 was not orthogonal to U2, what would go wrong? Well, the projection from V4 onto one of those vectors might have a similar component in this direction. And then when we are subtracting it off, we can actually sort of undo some of the work we've done in the first steps, if that makes sense. Because, right, when we are projecting, not only are we taking the dot product, so this sort of scalar multiple, but we are also then having that extra component, right? We have that. Let's see, let's pull up our notes from the previous one. We have that scalar multiple of the vector of the direction we are looking at. And then this one, now we're in the direction of U2. But if these two are not mutually orthogonal, they're going to share certain components, certain directions. And so maybe if I try to do this step when I'm subtracting off a component in one direction, I can undo or screw that part of the computation up if this vector isn't orthogonal to that. If this vector shares some components with this guy or shares some direction with this guy, well, then when I subtract off this projection, it's going to mess up the work we did previously. So think about that. And so as long as the basis vectors, or I guess we should say the spanning set, the linearly independent set, is at least orthogonal, we won't do that. So I'll just kind of summarize that. We need an orthogonal basis for W to easily calculate components of Y in W, namely this parallel component. Right? We want to think of this parallel component as just the projection of Y into W. So our Z, another way we could write that as our Y perpendicular, we could write it the projection onto W. And now W is a subspace of Y. This is really what we want. So how do we do that? Well, it's going to be exactly this process. So this gives us our formula for Fourier expansion. So given an orthogonal set let's call it U. To U1 up to UM. And some X. Let's see. So there's a couple ways we can introduce this. You know what? Let's call this an orthogonal. Let's make two definitions. Let's just start off with our orthogonal basis, U. So U1 to UN of Rn. So it is a full basis. We have a fully maximally linearly independent spanning set. And X just any arbitrary vector in Rn. Then X is going to be, well, in some sense, you can kind of think of this as our standard basis. If we write, write numbers, when we write numbers, I kind of want to, let's make a little scratch work area here. When we write numbers, 2, 3, -7, 5, really what we're saying is if this is a vector v or x, we're saying if I project x onto E1, we would get 2. If we project x onto E2, we would get 3. Namely, the scalar components of x are the projections of x onto these standard bases. But if we potentially have a non-standard basis, at least if they're orthogonal, we can kind of mimic that same process, this process we've been talking about. How do I find the component of x in the direction of U1? Well, it's just going to be the projection onto U1 of x. Sorry, let's say UI. And then we do that for each vector. In other words, if we wanted to write out our formula, how do we project? We would take the dot product of x with whichever basis vector. We want to make sure it's normalized. And then, of course, we want it in the direction of that basis vector. So this gives a linear combination of x in terms of the basis U. For a subset, let's call it W, and actually a sub space, so it is a vector space of Rn with, let's call it an orthogonal spanning set. Why am I calling it spanning set? Orthogonal basis. Doesn't necessarily have to be orthonormal, but let's just call our bases out now, W1 up to Wm. Then we'll call it x parallel, or we can call it the projection onto W of x, is just going to be the components of x in those directions. I equals 1 to m of the projection to Wi of x. So it's essentially the same formula. Rx dot wi over wi squared in the direction of wi. So easy examples. And where you should draw the analogy. If this is our v, and we want to say project v onto the xy plane, well, the xy plane is spanned by the first two, by our e1 and e2. So that's pretty easy. The projection of v, we can call it onto xy of v, is just going to be 3 minus 2. Moreover, if we want the distance between v, or the point represented by v, maybe we should write it a little more formally as the distance between now the point 3 minus 2, 5, and the xy plane. Well, what's that going to be? We want the length of the orthogonal component. How do we find the orthogonal component? That's just going to be v minus the parallel component. And of course, we take the norm. And so that, easily enough, is going to be the norm of, well, the, parallel component. What's the parallel component of this? Well, it's the component in the direction of the xy plane. If we were to sort of sit that component within R3, I guess more formally, since we are considering our xy plane sitting inside R3, we should include that third coordinate, our 0. So we are just getting rid of the z coordinate. So we would just subtract this off, and of course, what are we left with? Well, we're just left with the z coordinate itself is the orthogonal component of v to the xy plane. And so, of course, the length, or the distance that point is just 5. That's where we want to draw our analogy from this. But now what's going to happen if I change the plane? If the plane isn't as nice as one of the standard coordinate planes, how do we work with that? So let's take a look. So let's let W be the plane. Given by x minus 2y plus z equals 0. What do we want to do? Find the point. Let's make a few parts. A, find the point on W closest to our points P, 1, 0, 3. B, find the distance between P and W. And then we'll have some extra parts to do. We'll use this same plane and same example I want to build on this a little bit beyond what the book is doing. But let's get through these first two parts first. We've only got a couple minutes left, so let's just at least get started, since we haven't quite seen a problem exactly like this. And I know there's a couple of you guys that didn't quite have Calc 3. So hopefully your intuition is a lot stronger now at the end of this semester in terms of this notion of dimension and degrees of freedom. So we've seen with row reductions, if I have 2 0 rows, when we do some row reductions, that gives us 2 degrees of freedom, meaning the subset spanned by the solution to whatever system of equations or whatever eigenvalues or something we're computing with that is going to be 2 dimensions. So the number of degrees of freedom you have with your choices of vectors gives you the number of dimensions. You also should start to develop a little bit of an intuition for equations, and that equations are being restrictions. So degrees of freedom, the more degrees of freedom increase your dimensions, whereas equations restrict your dimensions. If I have 3 systems of equations with 3 variables, how many solutions are there? If they're all sort of linearly independent, well, we have a one-dimensional solution, right? If I have 3 linearly independent, truly unique equations, then I'm starting from a 3-dimensional space, and every equation restricts our dimension down by 1. So if we start with a 3-dimensional space, x, y, and z, and have one equation, one restriction, if we were to set this up as a system of linear equations, how many degrees of freedom would we have? 2. So we can define planes, a 2-dimensional plane in 3 dimensions, by simply one equation. How would we find spanning vectors for this set, though? So we know that W, since we have restrictions, we can pick 2 degrees of freedom. Let's say our x and y, we can pick those to be anything, but as soon as we pick x and y, our z has to be chosen so that it satisfies this equation. In other words, if we're picking x and y as our degrees of freedom, this is going to force z equal to minus x plus 2y. So z is going, or excuse me, w is going to be the set of all vectors of this form, where a and b can be chosen freely. So if you kind of separate out the a's and b's, you can consider it as the span of a. Where do a's appear? In the first and third column. First one we have 1 multiple of a, third one we have -1 copies of a. And then likewise our b's. Sorry, that should be a 1 and a 2 here. And so I guess we don't need span here since we're taking all linear combinations, but really what is implied by our span is that we can reduce our basis set or our spanning set down to these 2 vectors. So all linear combinations of these is essentially what we mean by this. And so we found a basis for W. So great, that's a good first start. However, what was the problem with our lead-in to this point, to this topic? We need to make sure that the basis is at least orthogonal, because if they're not orthogonal, we can't necessarily do projections correctly. So our next step is going to be to create an orthogonal basis for W, and then we can answer those 2 questions quite easily. Any questions?